Uh, Good evening, everyone. My name is Amay Dukle. I am. I welcome you to the first live interactive session for brief introduction to microsensors course. The course code is NOC 25 E01. I hope I'm audible and my screen is visible to everyone. So we'll start with the. So before we begin, a brief introduction about what the course is and what I am. So basically, the course is being conducted by ISER Bhopal. Professor Shantanu Talukdar, Assistant Professor in the Department of Electrical and Computer Science, is the course instructor. My name is Amay Dokle. I am a Prime Minister Research Fellow in the Department of Mechanical Engineering, IIT Tirupati. So basically, I'll be taking on the live sessions. So on Monday, the live sessions will be taken by me. On Friday, they will be taken by Mr. Vishal. So basically, what will happen is both the sessions will run parallelly. It is your choice whether you want to listen to his sessions or whether you want to listen to my sessions. In case you are not able to attend the sessions, you can also visit the sessions using this YouTube link. So the link also will be provided in your course webpage. So before we begin, some of the basic things like for every session. So it is basically to boost your performance. It is not compulsory. Uh, it is like it is highly encouraged, but it is not compulsory. What we will be doing is we'll be solving previous year assignments for helping you guys. So again, be respectful in the chat. You can ask the questions at the end of the session, or you can ask the question when the problem is being solved. I'm cool with both, whichever way you are comfortable with. So basically, coming to today's session plan, I'll revise some important concepts. Then we'll discuss practice assignment 0, practice assignment 1, and then we'll discuss previous year assignment 1. So basically, by solving these many questions, I hope you will be able to solve this year's assignment. And then we'll move to the question and answer session. So the course outline is this is a 4 week course. So there'll be four sessions each for each week there'll be one session, and at the end of the 4 weeks there'll be one revision session, wherein what we'll be doing is we'll be revising all the problems that we have solved in the first four sessions. So if you miss these sessions, you can attend the last practice session where you will be able to um, revise everything basically. So like so is there any questions from your end? So before we begin with the session, is there any like non-technical questions from your end? So since nobody is responding, I'm taking it as a know that you don't have any questions. So I'll just switch off my camera to save some bandwidth, and we'll proceed with the session. So basically, the first since course is basically brief introduction to microsensors. So there are the two main important parts in this course actually. If you see, one is micro and another one is sensor. So first we'll start with the sensor, which is a part which many of you are well aware of. Basically, sensor is basically defined as a primary element in the measuring chain, which converts variable, generally non-electric input into suitable measurable measuring signal, especially in electrical form. So basically, it will be like you can have any type of sensor. You can have a pressure sensor, you can have a force sensor, you can have an accelerometer. So basically, what it does is basically a pressure sensor will measure pressure. So it will what it will do is basically it will measure pressure and it will convert it into electrical signal. So it can be the change in resistance, or it can be a like something like that. So if it's a piezoresistive sensor, what it will happen is uh, change the resistance. So when the pressure increases, the resistance will change, and you will get the uh, say sensing output. So one thing which is very important to note in sensor is basically sensor never gives you a like an absolute value. It will always give you a relative value. So whatever you are getting value, if you like if you take a pressure sensor, so what you are getting the value will be with relation to one atmospheric pressure. So that is something which you need to understand in mind when you are thinking of a sensor, or when you are applying a sensor in your day-to-day application. Um, so now, since we are well aware of what sensor is, so we'll go into what the micro, the first term, what micro means. So what from here you can see what the scale looks like. So
Sir, good evening, sir. Please make the slideshow, sir.
you are not able to see it. Is it fine now?
Okay, sir. Okay, sir.
Is it fine now? Yeah. So so here you can see like how the scale looks like. So uh, my macro systems is basically what you are well aware of. So basically that is about 10 millimeters. So meso system is basically which is between the meso and the micro systems. So basically these are like between 100 micrometer and 10 millimeter. So these are something which have been in place for a long time, and which are also like even now uh, when you are having a micro system, you have to use it in a real world, you have to have a meso interface. Like you have to have something which is at like the packaging. So basically if you take a sensor, so even though the sensor will be on the micro scale, the size of the sensor will be micro, the packaging will be at the meso scale only. So yeah, it will there'll be a casing or there'll be something like that that will protect the sensor. So something like micro system. So that is between basically 1 micrometer to 100 micrometer. Then it will be basically the meso system, which will be the casing or something like that, which will always be present. And there is the macro system which we are using, which we are very much used to using. And here, basically less than 1 micrometer will be the nano scale. So that will be basically atoms, basically the biological systems, if I may. So those are something which exists at the nano scale. Also, there are nanoparticles and many other things. So that's again not some. That's a topic for another discussion. Our scale will be basically in the micrometer scale. So that is maybe 1 micrometer or zero point 0.1 micrometer, and maximum up to 100 micrometer. That range is what we are talking about. So uh, why basically why so next, coming to why mems are important. So basically you can see from the market forecast. So in the year from 2015 to 2021 itself, the market has basically doubled. Approximately it has doubled in less than 6 years. So you can see from 10 billion dollars it has went to 20 approximately $20 billion in less than 6 years. So you can see how the market is growing. And so basically the usage of mems is increased in every field. So basically you take a car, you take your mobile phone, or you take anything, the usage of mems based sensor has increased drastically in every field. So you can see that it is a growing field, so it is very important to have some knowledge of mems for you. So, what are the applications of MEMS? So, coming to the applications of MEMS. So, basically, one is basically if you go at the biomedical level, this is the micro needles. So, basically, micro needles have been developed for many people will have typhanophobia. Typhanophobia is basically the fear of needles. So, when they see the needle, they'll faint. So, that is something which is very common, like not very common, but it is common. So what happens is, so as not to have that fear being triggered in the people, there people have come up with micro needles. Basically, micro needles will be like a tattoo or something very it will be painless basically. So it will be used for like intradermal transdermal drug delivery. So basically, what will happen is they'll paste microneedle like a tattoo or something, and then the microneedles will dissolve, or microneedles will basically deliver the drugs, dissolve and deliver the drugs, and basically it will be painless, and it will not have even a mark on the body. So that is something which is a very like upcoming new and upcoming field. During basically COVID, when the everyone actually had the vaccine had become compulsory, a lot of research came up in this direction. So then other things, there are gas sensors, basically not in India but in many other countries. These are compulsory basically in any establishment. Uh, so if there is any leakage or something like that, so to gauge that or to detect that, these like systems have become compulsory. Uh, so then there is motion sensors now. Every mall you can see that the doors are automatic. Doors do not require you to touch them. So those kind of things are basically motion sensors. Those things work on motion sensors. So how they work is basically it's a very interesting way how it works. So basically, when you move, you have the air in your close vicinity. uh, it pushes you push the air basically, and that basically leads to your motion being detected by the sensor. So it's a very interesting working. If you get time, basically have a look at how it works. So again, the force sensors, as I said, pressure sensor, like anything which is used basically for sensing, force sensing applications. So basically, mainly it is a pressure sensors is what we are talking about, but there are other type of sensors as well. So these are the major sensor application of MEMS based sensors basically. So why? So now since we know the application, now we come to know like why MEMS. So we could have used the normal sensors also, right? We can use a micro scale sensor. And why are we coming at the MEMS level? So basically, what you can see. So from here you can see that when you scale down something, basically you need less space. So when there is less space, there is less heat being generated. So it provides like good thermal properties. It provides like very good efficiency. So basically, the electrons, if you are having a so per se, just take an example of your CPU, which you are having in your computer or the processor, basically. So earlier, when it used to be a big scale, when the transistor used to be a very big transistor, so what would happen is a lot of power would be required to push the electron from that sensor. So basically, from that transistor. So now, since the number of transistors has increased, but the size of transistor has reduced, so the number of electrons needed is less. So the power requirement has become less. So that is how the thing works. The you can get more work done at using a smaller device. So basically, that is why scaling is what we are doing. So scaling laws are very important. You will learn about them in the class in this week's lecture. Also, you might have learned about them. So how scaling actually works. So it is a very efficient way of um, finding out how like net system work actually. Basically, how you can relate. So basically, how you can correlate what is happening at the macro scale to the micro scale using the scaling factor. Basically, how that is why the scaling laws are very important. And the next thing which is there in this class is how a sensor actually works, how the measuring chain of a sensor actually works. So basically, an external force is applied, then we have a moving structure, basically a cantilever or a membrane. Then the moving structure is deflected, so you see a deflection in the moving structure, and then you measure the deflection, and then using the deflection you calculate the value. So as I said earlier, we are not calculating the absolute value. We actually, whenever a sensor is there, you always see a change. So external force, so basically it's at rest, some force F is coming. um, so what the measurements you will get, will be relative to the rest position. So that is how the measuring chain works, or that is how a sensor per se works. So this is how you can look at working principles. Basically, here we have a force sensor. So here, what is happening is we are applying a force F on a beam. So beam is the measuring element. So beam is the moving element. Sorry, beam is the moving element. Here you can see. Then there is a sensing element. So what will happen is when the force F is applied, there will be deflection, and that deflection will be sensed by the sensing element. So basically, that what deflection is sensed by the sensing element, that will be converted by using this governing equation. So basically, by using this governing equation, you will be able to. So what will the sensing element do? It will calculate the x value. K value will be calculated while the fabrication has been done. So when you are designing the sensor, or while you are fabricating the sensor, you get the K value. You are finding the X value. So then you eventually what you get is the F value. So that is how the sensor actually works. So now, coming to something which is there in this class. So how you find the deflection? So to find the deflection, you need, so your basic principle in this class is basically finding how the x works. Okay, so how the k is, how the value of k is found. So for finding the value of k, you need to know a bit of formulas of how to like resolve a, uh, resolve a beam into its components. So basically, depending on how the beam is attached, so basically, if it is support, if it is fixed from one side and free from the other side, this is how it's the force are resolved. If it is fixed from both the side, this is how the force are resolved. If it is fixed and pinned from one side, then this is how the force is resolved. So you can see from every side, you can see how the force solution works. Okay, so I hope there are no questions. But in case you have any questions for from the revision part, you can just unmute yourself and ask any questions. Okay, so you can ask questions at the end as well. So I'll just move to the assignment. Okay, so this is the week zero practice assignment. So basically, the first question is, assume a parallel plate capacitor is having a charge C. The charge stored in the capacitor is Q. If the voltage across the capacitor is V, then, so basically we have to find the relation between the voltage and the charge. So basically it is asking here, so what will be the relation? So will it be V is equal to Q upon 2C square, whether it will be V equal to C into Q square, whether it will be V is equal to C into Q, or whether it will be V is equal to Q by C. Okay, so any guesses, any answers from your end?
D, sir.
Okay, so great. So this is basic, very basic question. So yeah, so basically the governing equation for a capacitor is Q is equal to C. So basically, whenever a capacitor is connected, it will be connected to there will be a charge will be stored. So basically, capacitor is provides infinite resistance. So whatever the charge is coming from whatever. So basically, what is happening is basically the electrons are coming from the power source, and then they are getting accumulated at the at one of the plates. So basically, what is happening is we all know that electrons basically move from the negative terminal to the positive terminal. So although the convention is positive and negative, the electron flow is from negative to positive. So from the negative terminal, when the charge is moving, electron is moving, it will get like accumulated at the plate. and then a negative charge will be developed at the opposite plate, and then basically uh, in the dielectric medium, so which is the medium which is there between the two plates, the capacitance has been developed. So the value of the governing equation for any capacitor is Q is equal to CV. Okay, so we'll move to the second question. So after the application of voltage V, energy stored in the capacitor mentioned in question one. So basically in the same question. So what is the energy stored? So basically we now know the governing equation of the capacitor which was asked in the first question. So now what we have to find out, what is the energy stored. So these are the formulas many of you might have learnt also. So again, we just go through it. So the first option is J is equal to CV square by 2. Where B is there.
Sir, present second question, sir. Sir.
Yeah, this is second question only.
And here it looks on the screen.
Okay, 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 okay. Yeah, yeah, yeah. So there is. I'll just stop and I'll restart again. Just a second. We are facing net problems in our institute. That is why I have stopped my face also. Video also have stopped. Just give me a moment, please. Is it question number two now?
Yes, sir.
Sorry for the problem. Uh, so yeah. So what? So in the first question, so assume everything is the same as in the first question. So now we have to find out what is the energy that is stored in the capacitor. So as I said, the electrons will be accumulated at one plate, and the opposite plate will be getting a opposite charge. So now what we are asking is what is the energy? So basically the energy so now when the electrons are being stored, obviously there will be energy stored, right? So what is the energy and how will you find it out? So what is the formula for that energy? So the options are J is equal to CV CV square by 2, J is equal to CV square, J is equal to CV by 2, and J is equal to CV. So uh, so just we are deriving it. So basically at any instant t, so uh, to transfer one charge from one plate to another, the the energy that is energy that is required is basically q is v dash is equal to q dash into c. So basically that is the like for one charge to being moved from one plate to the another plate, we need that much of that is the potential difference that is needed. So basically, for actually doing the entire transferring the entire charge that is there on the from one side to another, what we'll have to do is basically we'll have to integrate the things. We have to integrate the potential difference into charge over the entire charge. So basically, for one charge, what the potential difference is needed, we need to integrate it over the entire charge. So basically, it's 0 to q. So q is the maximum charge on the capacitor. So basically, from that, what the equation we get is equal to half q square by c. But then what the thing is that q is equal to cv. So we know already from the previous equation. So the answer from, because we don't have any equation with any option with q as an option. So we don't have q as an option in any of the uh, q, as a variable in any of the options. So that is why we use the equation q is equal to cv, and then we get the final answer as q is equal to half cv square, or j is equal to half cv square, or j is equal to cv square by 2. Anyone has any questions? Okay.
Sir, some of us are from the basics of electronics, sir. So just make the statistics and whichever part is a tough one, it is better to discuss that one, sir.
Okay, so what the thing is that mine, I've been instructed basically to take all the previous year questions. So if you have seen Vishal's session, so basically that is basically focused on the electronics background. So if you already have the electronics background now, I would suggest go through his session because he's having more of higher level things. So my thing is, since my background is mechanical, my
Okay, sir.
lectures are focused for those people. So basically, as you know, the requirement is basically anyone can register, right, ma'am?
Yes, sir.
So what is done is, so the plan is there. That is why there are two sessions. So basically, the ones where Vishal is taking, there will be like more of that is suited for more of electronics background. If you are from the non-electronics background, you should like you can come for my session because mine will be a bit like dumbed down session, or you can say more simpler sessions. So
Yes, sir. It is true.
my slides will be available. So whenever I would suggest you attend his sessions completely, and my slides you just take them and just go through them from the link, so you don't have to actually see the lecture. So what I would suggest is you do one thing is you just take the slides, you will get the link. So from that link just take the slides and just go through them and just like for your revision per se. Otherwise I would say like my sessions will be dumbed down for a electronics background, so I would not recommend electronic background to join my sessions. I would rather suggest you join Vishal session, and if you have a non-electronic background, join my sessions because mine will be a like from the basics I'll be going. So it's that's what my suggestion is. So
Sir, where is the link, sir? Where is the first day link, sir?
you will get in the NPTEL when you join the course page, just at the um, left bottom, problem solving sessions, Jan.
Uh, Often I have seen, sir. Still, it is not uploaded, sir.
Yeah, it will take some time, like 2 3 days. You just wait. But by the end of weekend, it will get uploaded. For us, the last day is Thursday, so please wait till Thursday for some. So, any other questions? So we'll move to the next question. So as I said, join. You don't need to waste your time because this will be a dumbed down session, mainly focused on non-electronics background. So I would suggest you join the sessions on Friday for like going into the higher level. So these are for the basic level beginners. So yeah, so that's how it is. So we'll move to the next question. So in the question three, a point charge Q is kept in the free space. Magnitude for electric field and electric potential are E and V at distance R from the point charge respectively. Absolute permittivity of air is epsilon naught 0. Then choose the right option. So basically we have to find the electric field and electric potential for the charge. Basically a point charge is kept in free space, and we have to find its electric potential, electric field and electric potential. So basically this is basically relates to Coulomb's law. So basically what happens is when charge is kept in field, kept at a point, uh, the electric field lines pass through it from all directions. So basically there will be electric field line that will be emanating from the point charge. So the formula for electric field is 1 by 4 pi epsilon naught q upon r square. R square is the distance between the point at which the charge is kept and the point from which we are calculating the charge. And basically the electric potential difference is basically you integrate the electric field over the length, over the distance, and basically what you get is 1 by epsilon naught q upon RB minus Q upon RA. So this is the answer. So Q upon 4 pi epsilon naught E naught upon R square, and uh, since here basically here we are taking the point, so basically we are taking RA as 0. So basically that is why in this in the answer which we will be getting is basically Q upon 4 pi epsilon naught R. So move, so anyway, move to the next question. So basically we have a rectangular beam as shown in the figure. It has length L and cross sectional area A. The left side of the beam is fixed at the wall. The beam is pulled using an axial force such that the length of beam increases by delta L. There is no bending or torsion in the beam. The material of the beam is having a Young's modulus of Y. Now answer the following question. The question number 4 is axial stress acting on the beam is FA, F, F by A, and Y. So basically, axial stress is basically the stress that acts through the central axis. So basically, when the force is being passed through the central axis, the uh, that is called as the axial stress. So basically, axial stress is basically given as force applied force upon area upon the cross section area. So basically, um, whenever the force is applied, so what happens is basically when you are applying the force, the molecules which are there inside the material that has the molecules in the material, basically they are they are being pulled apart basically. So when they're being pulled apart, sorry for the inconvenience. So basically, when the axial force is applied, the molecules in the material are being pulled apart. So when the molecules are being pulled apart, what happens is a stress is developed between them. So basically, whenever anything is pulled apart, they have a tendency to come together, right? So basically, when there is basically for that to counter it, uh, counter the force, something is developed internally so that it can stick together. So what is developed internally is called as stress. So basically, stress is the force upon the cross sectional area, and the strain is basically the change in length upon original length. So basically, stress is given by option C, F by A. In the next question is basically what is the strain? The strain is basically, as I said, change in length upon original length. So that is delta L upon L. So now, what is the Young's modulus? So basically, Young's modulus. So the basically what is happens is stress is proportional to the strain. Is what within the basically I'll give you comfort. So basically, this is something that's called as stress strain curve. So basically, what happens is over the x-axis, it's the strain, that is the change in length, and over the y-axis, it is the stress that is applied. So basically, when the force is applied, what happens is the material is getting pulled apart, right? So, like in the starting, so basically, when you can see in the yellow, in the zone or in the orange zone, basically in this zone, the amount of force which you are applying, basically that is equal to the that is proportional to the change in length you are getting. So more the force you apply, the more there will be a change in length. So after a point, so basically after a yield strength, so basically what happens is at the yield strength point, so yielding happens. What is yielding is basically the bonds between some of the materials, some of the molecules break. So what happens is when the bonds between some of the molecules break, it becomes easier to uh, break the full material apart. So when if there is even one like one uh, point that has been broken, so one since one point is done, so then you can just like even if you are pulling a paper or something, till you are having the paper is intact, you have to put a lot of energy to like tear it apart. But once you have even a small crack or a small tear on the paper, and if you pull it, you require less force to actually uh, tear the paper apart, right? You might have done that experiment, you might have noticed that a lot. So that is something which is happening. So at the yield point, what happens is basically the the force required basically becomes lower because some molecules have become have started breaking apart. So then so then with less force being applied, so less incremental force. I'm not talking about the less force per se, less incremental force. So earlier, if you had to apply 10 newtons to get 10 millimeter of deflection, so I'm just giving you an example. If you had to apply 10 newton to get a 10 millimeter of deflection, after the yielding point, you have to just apply like 1 newton to get 10 millimeter of deflection. So that is how you can see the changes happening. So then the it reaches the maximum stress at maximum strength. So basically, it is the maximum stress that the material can withstand. That is called as the ultimate strength. And the fracture is basically when the material breaks into two. So that is how the stress strain curve looks like. So, so as per the Hooke's law, within the proportional limit, so that basically the limit that has been the area that has been given in the orange section, uh, basically stress is proportional to strain. So the constant of proportionality, that is the slope of this line, is given as the Young's modulus. So I hope I'm clear.
Yes, sir.
Yeah. So yeah, we move to the next question. This is basically the easiest question. So voltage V has been applied across the metal wire having electrical resistance R. Then the current through the wire is V by R, VR, V square by R, or R by V. So basically, it's the Ohm's law, which we studied from the fifth standard. So basically, V is equal to IR. So basic Ohm's law. This is the triangle. You can maybe if you are um, like if you want to remember properly, you can use this triangle also for your reference. So the answer is option A. I is equal to V by R. So now moving to the eighth question. If two charges Q1 and Q2 are kept at a distance D, then the force between them is found to be F1. If we increase the distance between them, between the two charges to 2D, the force is now F2. So now what we have to find is the ratio of F1 by F2. So whether it is 4, 1 by 2, 4, 1, 1 by 2 or 2. So basically we had this formula just two, 3 questions before. So if we are finding out between the forces, basically to 1 by 4 pi epsilon naught. So here we are, since we are having only a single charge, we are having Q. So basically 1 by 4 pi epsilon naught Q1 Q2 upon R square. Basically that is the formula. So here it is. You can say that when the two charges are there, so the force acting between them is basically 1 by 4 pi epsilon naught Q1 Q2 upon R square. So R is the distance, Q1 Q2 is the charge, and 1 by 4 pi epsilon naught is the constant. So basically, when we are changing the length by 2D, so basically what is happening is R square is becoming so when you divide F1 upon F2, basically what will happen is Q1 Q2 will be the same uh, upon D, and basically it will be like Q1 Q2 upon 4 means like D square upon D square will get cancelled. So what you will get is the answer is 4. I think so it is very simple to know. We have to use only this formula. We have to divide everything and you'll get the answer. So with this, we have finished the week zero assignment. So basically, these were the very basic questions which you needed to know before joining the course. So these are the actual course related assignments which we will start now. Okay. So starting with the week one assignment. So um, what is the correct workflow of a MEMS force sensor? So basically, we are having a MEMS force sensor, and we want to find out what will be the measuring chain. As I explained earlier, how will you get the measuring chain? How will the measuring chain look like? So the option A is external force, moving structure, deflection of the moving structure, calculate the applied force, and measuring of the deflection. The question B is external force, calculate the applied force, deflection of the moving structure, measurement of deflection. External force, moving structure, deflection of the moving structure, measuring the deflection and calculating the applied force. So, and option D is basically moving structure, measuring deflection, external force, deflection of the moving structure, calculating the applied force. So basically, this is how MEMS working chain looks like. So basically, whenever you have a structure, you have to get the external force on it. So once the external force is applied, you will see there is a movement on the structure. So basically, there will be the cantilever or the membrane that will be moving. So once the moving structure is moving, then you calculate the deflection, and from the deflection, what you get is the force. So basically, the answer is C. So we have the external force. You have a moving structure that is the beam or the cantilever. The external force is falling on the beam or the cantilever. Then you are having the deflection of the moving structure, and then you measure the deflection, and then you calculate the applied force. So that is how a sensor chain looks like. So the next question: what is the critical length of a glass cube having density 2500 kilogram per meter cube to float in a fluid having a surface tension of 27.56 millinewton per meter? Neglect the buoyancy force acting on you. So basically, just taking up uh, this taking a free body diagram. So basically, what is having is we are having a block of like metal or something which is floating in a liquid with a very high surface tension. So basically, normal surface tension of water is like 1 millinewton per meter. So we are having 27 millinewton. So now what is happening? Surface tension is basically the force that the liquid exerts to go up, right? And weight of the block basically always comes down. So now what is the critical length is basically the length so at which the floating will happen. So if the length of the block is bigger than the critical length, then only it will be able to float, else it will sink. That is how the concept works. So basically, you have critical length is basically you are having that the minimum size of the cube so as it only floats and it doesn't go down. So if the length is very small, if the block is very small, even though um, like that will still sink inside the liquid. So that is how it is working. So what we have to do is the surface tension force should be greater than the weight of the block, right? So what we are finding out is that the critical length basically the surface tension force is given by 4 uh, 4 gamma L, and the weight of the block is basically volume into gravity. So basically rho into L cube into G. So basically then we get the formula of get the equation for the critical length. So that is 4 gamma upon rho G, that is equal to 2.12 millimeter. So we have all the formulas here. We have the rho given here. We have the surface tension, that is the gamma, given here. Um, and gravity obviously we all know, and from that by substituting that in the equation you get the critical length.
Sir, how 4 gamma L will come, sir, for surface tension?
That is the formula for surface tension, basically 4 gamma into L.
Okay, sir. Okay.
So that is the basic formula for the surface tension force. If you search on Google, you'll get it. Uh, so that is the formula. So these are the formulas. Some formulas you need to remember basically. So for surface tension, it is 4 gamma L, and so for weight, obviously it's volume into gravity. Um, so so mass into gravity. So that is mass into volume into gravity. So basically that you're doing. Density into volume into gravity, what you're doing basically. And that when you substitute all the parameters, you get the answer as 2.12. So we have the third question. The block is hanging vertically downward by two parallel beams of width W, length L, and depth H. The beam material has elasticity of what will be the equivalent spring constant of the system. So basically, what is happening is we have basically you just have to think that it has a spring. So basically, we have two springs holding a mass. So now there is a concept of parallel and like series in spring. So basically, what happens is in the resistance, basically what you do is you calculate the like the potential difference basically. Here, what we calculate is basically uh, the deflection here. So when the deflection is same, you like you add the spring constant. When the deflection is different, you basically do a like you have the parallel. What you have the so basically for the electronic guys to remember, when the springs are in parallel, use the resistance series. So how you when you have the series in the resistance in series, you add the two resistances, right? So in the same way, when you have springs in parallel, you add them. You add the spring constants, and when you have the springs in series, use the parallel equation. So basically, for all the electronics guys, it is opposite of the ohms. Like the series and parallel are opposite for beams and springs. So springs and resistances, the formulas are opposite. So what is the formula for resistance in series? You have that for springs in parallel and vice versa. So that's one thing. So here we have the two springs here. We are having a free body diagram basically. So we have the total spring constant is basically 2 into K. So the formula for K is WHE upon L. So basically, L is the length, H is the depth, and W is the cross sectional area. As you can, is the width of the sorry, it's the width. Then H is the depth. So that is basically W into H. You get the cross sectional area. Width is W, and H you get the cross sectional area. E is the like the elasticity modulus, and the L is the length. So this is the question. Any doubts?
Sir, now the force is along the length, L is coming in the denominator, sir. Is it a shortcut to remember?
No. So this is so the formula for K is basically cross sectional area into elasticity upon the length. So for any elasticity, the for elastic constant, the formula will be the same. So so you can
Now
say
here the force is uh, in the along axial direction, along the lengths now, sir. So
yes.
that's why will it come L as the denominator?
No. There is no shortcut. Actually,
Okay.
here the basic is whether the springs are in parallel or series. So basically, when the force is equal on both the springs, it is coming as parallel. So here, what you are seeing is you are having the springs in parallel. That is something which you have to find out. So the formula is L has no relation. So even if the springs were in series, you will get L in the denominator only.
Okay, sir.
Okay. So what will be the formula when it is in series? It will be 1 by k total is equal to 1 by k1 plus 1 by k2. So what you have in resistance in parallel, you'll have the same formula for spring constant in series. Okay. So spring constant and resistance are like interchangeable, like what like opposite to each other. Basically, the formulas. Okay. Any other questions? Okay, so we'll move to the next question. So this is a basic question, which is like a logic-based question. It has nothing to do with like the course per se. It is a very logic-based question. So we have a matchbox basically that is 50 long and has a cross-sectional area of 4 millimeter square. So now assume that each matchstick has needs 1 millimeter square of surface coating on the matchbox for ignition. Considering the matchbox has a size of 50 mm into 30 into 4 So, is there enough ignitable area for all the matches it can enclose? Have exactly the same area to ignite all the matchsticks? Not enough area to ignite all the matchsticks? Insufficient data? Have more than enough area to ignite the match? So basically, um, just before we actually move into this question, these questions will be like these are some questions you can expect in your exam. So basically, what will be let's just to give you an overview of how your exam will be. So basically, passing will be everyone's. Like even if you like use your only your brain and you don't study, also will pass it. So like passing will not be a very big thing. Like passing will be very easy for everyone. Like even if you have done your basics right, you will pass. Okay. So then there'll be like from 60 to 80 I'm talking about. So 60% everyone will pass. So 60 to 80 will be basically how much you study. So how much you study now? So the assignments, if you do properly, how if you go through our lectures, whichever there, if you go to the lecture slides properly before the exam, you will get you should get at least 80. And if you retain everything, and if you work like if you do it properly, you should get 80. So these are the questions that will determine whether you get the 80 or the 95. So basically, these are the questions which will be given. Like these will be some kind of googly questions, which will make you think like 2 or 3 times. Like you have to use like 2 or 3. You'll have to do some calculations basically. So you'll have to use your brain and you have to do some calculations. So that is going to be the difference between the 80 and the 95. These questions basically these are the type of questions. I'm not saying that this question will come, but these will be the questions which will be the determining factor. So but as you will see now, the questions will be very easy. So if you read it properly and if you just think for 1 minute, you'll be able to get these questions right. So many times in exam students just leave the questions or just bluff on the questions. Don't do that. Just try to read it twice or thrice. You'll have an ample time, so just read it twice or thrice. You'll get the answer. So now we'll move to the solution of the question. So what we have to do is first, since the number of matches has not been given, what we need to do is what we need to find is the ignitable area okay for the matches. So first we need to find out how much matches can be there in the like. So without knowing the number of matches, how will we actually find out like whether the area is sufficient or not? So what we do is basically we find the volume of the box and we find the volume of the single match and then we divide. So in one box there can be 30 matches, max to max. Okay. So then whether then we find out how many matches can be lit from that box. Basically that will be the coated area upon the like whatever area is required for one match. Okay, so we have the coated area and we have the like area that is required for one match. So here we have given. So assume that each matchstick needs one millimeter square of the surface coating. So we already know how much is the coated area. We know how much is the um, area needed by one matchstick. So then we can light approximately 120 matchsticks. Okay. So we know from the answer there is more than enough area to ignite all the matchsticks. So from looking at the question first, you might think that it is difficult, but it is a very simple question per se. So anyone has any questions? Okay, so we'll move to the next question. So we have a cantilever beam of length L with beam left edge made of an material with Young's modulus Y. It has a fundamental natural frequency of f1. After scaling the width to alpha b and depth to beta h, its natural frequency changes to f2. Calculate the ratio of this frequency f1 and f1 is to f2 if the values of alpha and beta are 10 raised to 3 and 10 raised to 4 respectively. You can use the frequency 1 by 2 pi k by m, where k is the stiffness and m is the effective mass of the beam. Again, where c is the constant and mb is the actual mass of the beam. You can also consider only the transverse vibration. So this is a very simple question. You have been given the formula. So you put basically the formula of f. So you get f1 by f2. So what is happening is we are considering that the mass is same, because already although the question doesn't say that, because when you are scaling and when you are scaling something, the mass will change. But here what we are doing is, since the value of c has not been given, so basically if the value of c had been given, we had to consider mass also. So since the value of c has not been given in the question, if you can see the question, the value of c has not been given. So what we are doing is we are just considering the mass as constant for both the beams. So when you substitute k1 and k2, basically we have the equation for k1. K1 is cross section area, that is w into h into e upon l, and the second is alpha into w, beta into h into e upon l. So basically you see that you can cancel everything out. You will only get be left with alpha and beta, and you have the values of alpha and beta here. So that is 10 raised to 3 and 10 raised to minus 4. So what you get is 10 raised to minus 7. And basically the answer should be like answer should not be like 10 raised to 4 exactly. It is less than 10 raised to 4. Is somewhere between 10 raised to 3 and 10 raised to 4. But since the option has not been given, and it will be like more towards 10 raised to 4, so we are choosing the answer as 10 raised to 4. So this is something which you need to understand. So even in the exams you will have some of these questions where you have to take approximation. So like if you have to take approximation, just take it. Okay. So any questions?
Sir, what is the answer, sir? Now, actually, in the calculation, in the,
Calculation is 1 by 10 raised to minus 7.
then
It will
that
be,
option is not there, no, sir. We
yeah,
have
that
to
is not,
remove the question, sir.
that's what I
We have
said.
to
That's what I said. You'll have to take an approximation. So it will basically the answer will come is to 10 raised to 3.5. That will be the answer basically.
10 power 3.5, sir.
Yeah, so
10
that
power
will be
3
the
point.
answer basically. So now you know the calculations, right? So everything is else is getting cancelled. You are only left with alpha and beta. So alpha is 10 raised to minus 3, beta is 10 raised to minus 4. So that is 10 raised to minus 3 into 10 raised to minus 4 is equal to 10 raised to minus 7, right? So since it's in the denominator, it will go up. So that will become 10 raised to 7. So 10 raised to 7, and when you are taking out the square root, you basically divide by 1 by 2. So basically 10 raised to 7 divided by 2 is basically it will come as 10 raised to 3.5. So but 3.5 they didn't give in the option. Maybe the question is incomplete. They should have mentioned the value of c also. but they didn't do it in the question. So that is why.
Sir, I have a doubt, sir. Here, transverse vibration. Please, can you draw the figure and can you tell me the transverse vibration here? We can also consider only transverse vibration.
Okay, so basically, I'm gonna check whether I can draw. Basically, my laptop is going bad. I'll just find the figure and I'll just show it to you. So, so I'm not able to share that screen. I'll just take one new slide. So here you have a beam, right? Is my thing visible? Hello.
No, sir, I do not able to see the slide.
I'll show it on the drawing board. I think. Okay.
I think you have not shared, sir.
Is it working now?
Ah, okay, sir.
Yeah. So if any problem, just let me know because there is some problem with the sharing when I do it. So yeah, bear with me. So this is the beam basically you are having. So basically, transverse direction. Basically, like transverse is basically up and down. So transverse will be basically. I'll find a uh, drawing only for you. So you can see here. So basically, there will be like three types of vibrations. Basically, one is the first one you can see is the longitudinal vibration. So basically, the axis, the central line axis across the central line. Is my screen visible now?
Ah, visible, sir.
Yeah, yeah. So these are the three types of vibrations basically. So the first one will be basically the longitudinal vibration across the central axis. You are being pulled. The mass is being pulled across about the central axis, and it is moving about that thing. So basically, it is what you can see in the car spring or something like in your pen spring, which you can see when you have your pen, the click type of pen. The kind of the motion which you see is basically as the longitudinal vibration. Basically, once you press it, obviously it's constrained, but the motion which you can see is about one single axis. So basically, that is called as the longitudinal axis. longitudinal vibration. Then there is the transverse vibration. Basically, this is what you can see in the pendulum clock. So basically, what you can see in the pendulum clock, or even most of the examples which we are going through, we are having transverse bending. So basically, in this is transverse vibration is basically concerned with the deflection. So for all the cases which we are going through, unless there is some pulling action involved. So when there is a pulling and change in the length, um, so when there is change in length, so what we saw in the previous question, in the previous strains, the stress and the strain relation. So when there is stress and strain relation, so then that time it is the longitudinal vibration. When there is the deflection, so when the force is applied and there is a deflection happening, there is a change in the there is angular movement, that is called as the transverse vibration. And then there is something called as torsional vibration, which is not there in any of the problems which you will see. But just to give you an example, basically what is happening here, um, the thing is you are moving it in one direction. So and when you are moving it, it is rotating like in a circular manner. So like when if you have any, like if you have a chain, or if you have a like chain in your if you have a gold chain or something, and then if you just like if you're you like move it across along the like in a circle, like a conical in a conical profile, like a ice cream cone or something. If you move it like a ice cream cone, the vibration that is happening is like if you moving a gold chain in a conical profile. Like something I'm like just for you to imagine, if something like that is happening, then it is the torsional vibration. So that is not concerned in this study. So mainly if it is a deflection, uh, then it will be a transverse vibration, and if it is a stress strain, if it is a change in length, it will be a longitudinal vibration as a part of this like uh, course per se.
Now, in this case, transverse vibration length is not changing, na, sir, here.
Yeah, length is not changing.
L is,
The length is constant. Here the length will be constant. Here the what the change will be in the deflection. So there will be a theta, angle theta, that will be changing. Are you able?
how theta is related to dimensions width and h, sir, W and H.
Theta basically that is basically stiffness. So I think I'll have to draw and show only. So um, basically just consider a beam here. Okay. So then basically it is getting deflected. So this one was the original beam, and what you are getting is the deflection, right? So now what is happening is the depending on the like the dimensions of the beam, if it is a very thick beam, so just imagine you are applying a force here, you are applying a force F here, uh, okay, you are applying a force and that is causing the deflection to occur, right? uh, so now depending on the thickness of the beam, so depending on the thickness, so if it is a very thin beam, so if it is a very thin beam, the deflection will be more, right? So what we are concerned with, so elasticity is a property of material. Okay, so elasticity is a material property. Okay, so what will basically determine the thickness, so whether you have a like beam with cross sectional area of 1 millimeter square and the beam with cross sectional area of 10 millimeter square. So if per se you have a system, if you have a beam, you are applying the same force. Which beam will deflect more? The beam with cross sectional area of 1 millimeter square or the 10 millimeter square beam? So you have the same material, you are using same material. Uh, what which beam will do you think will deflect more? The 1 millimeter beam or the 10 millimeter beam? The cross section area is 10 millimeter. The length is same, everything is same. Just the cross sectional area for one beam is 1 millimeter and the other beam is 10 millimeter. So which one would be do you think will like deflect more? You're getting I know there is some problem from so basically depending on the cross sectional area, the 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 deflection changes. So that is why the elastic constant is related to the cross sectional area. So that is why you're getting the W and H in your equations. Okay, so now moving to the graded assignment. So this was the graded assignment which you had previous year. So if you had given the course previous year, last year, this would be the graded assignment which you had to submit. So we are just solving it for your reference. So here you have a rectangular bar of length 100 micrometer, width is 10 micrometer, out of plane thickness is 20 micrometer, which is fixed in on one side and other on the other end it is free. The Young's modulus E is 150 gigapascal. If the force 30 micronewton is applied on the axial direction in the x-axis, find the stress in megapascal and the stress in increment. So here you can see the stress is being applied in the axial direction. So what will be the axial direction? Basically, it will be um, along the length. So basically, when you take it out, so this is the case of longitudinal vibrations per se. So obviously there is no vibration here. Here we are directly deformation. There is longitudinal deformation. So along the x-axis, the force has been applied. So what law will be applicable? So we studied this law just a few slides back. What will be the the conditions? What will be the formulas which will be applied? So there will be the axial stress formula. So basically F into cross section area, that is W into H. So basically since the cross section is W into H, that is concerned. We are not concerned with the length. So we are only concerned with the cross section area because it's the axial stress. So the formula will be F into F upon W into H. Then the what we answer we get is 1.5 megapascal. Then the strain applied. So basically the strain is the stress upon the Young's modulus. So as I said, Young's modulus is basically the proportionality constant between stress and strain. So within the proportionality limit as per the Hooke's law, stress is proportional to strain. So we have the stress here. We have already found out the stress is 1.5 megapascal. We already have the Young's modulus as 150 gigapascal. So then, by substituting the value of strain we get is 0.0001. So now what we have to find, the last thing is basically we found the stress, we found the strain, and then we have to find the change in length. So what is strain? Basically, we know that strain is change in length upon the original length. So the change in length is basically delta L upon L. So we already know the strain, we already know the initial length. So now the change in length is basically strain into the original length is basically one what you get is 10 raised to minus 11 meter, or that is 1 nanometer. Any questions? Okay, so moving to the next question. So again, we had the same thing. So here we are just having a the sensor is being named as a piezoresistive sensor. So basically, we have two types of sensors. So piezo is basically when the force is applied, you have two kinds of things happen. Two kinds of material. So one are piezoresistive material, and other is piezoelectric material. So can anyone tell me what is the difference between piezoelectric and piezoresistive material? Can anyone tell me?
Piezoelectric means it will generate the charge, sir. Piezo resistance means it will change only the resistance or internal resistance. Sir.
Yes, very good. So basically, that's many times people get confused. So basically, piezoresistor and piezoelectric is basically piezoelectric. The pressure is applied on the piezoelectric material, and there will be a change. There will be a change in the crystal structure basically, and because of the crystal structure change, there will be a charge being generated. And in the piezo resistance, when you apply the force, basically piezo resistive materials are more common. Piezoelectric materials are not very common. You have to find them, and they are very expensive. Piezo resistive materials is basically in many of the materials. So basically, even in the normal material, if you have length, so what will happen is basically when you have apply force, what will happen is there will be change in length. So obviously there will be deflection, there will be change in length. So when the length increases, obviously the resistance increases. So basically piezoresistive, many materials can be used for piezoresistive application. Piezoelectric is basically you need there are very specific materials which are there for piezoelectric application. So now here we are having a piezoresistive force sensor. Basically the sensor is you have a beam. Over the beam you have a wire over and when the beam is deflecting, the wire's length is changing, and when the wire's length is increased based on the deflection. So if you are applying uh, 2 Newton of force, the deflection will be less. With 10 Newton, the deflection will go on increasing. So basically the length of the wire will go on increasing, and you will have the resistance will change accordingly. So what will be the change, the workflow of a piezoelectric sensor? Basically, the first question is external force on any moving structure like cantilever with piezoresistive material. Moving structure is deflected, measuring the change in resistance, calculating the deflection, calculate the force, resistance changes. Uh, External force on any moving structure like cantilever with piezoresistive material. Moving structure is deflected, resistance changes, measure the change in resistance, calculate the deflection, calculate the force. uh, External force on any moving structure like cantilever. Moving structure is deflected, calculate the deflection, resistance changes, measure the change in resistance, calculate the force. uh, like last option, basically external force applied on the moving structure, resistance is changing, moving structure is deflected, measuring the change in the resistance and calculate the deflection, calculate the force. So the answer is basically you have the external forces uh, is applied on the moving structure. So the moving structure is deflected. So because of the deflection, there is a change in the resistance. So from the sorry, the answer is wrong basically. The answer has to be measure the change in resistance. The answer has to be B. So uh, sorry, sorry for my bad. The answer has to be B. So you have the external force that is applied on the cantilever. The moving structure is deflected. The resistance changes. You measure the change in resistance. Then that you from that change in resistance you calculate the deflection, and then you get the force. Basically, that is how the sensor works. Question number three. Consider a cubical block of side length L made of material of density rho. If the length L is scaled over the pressure P due to the weight of the block on the surface varies as. So basically, here we are taking out the scaling law. So basically, what you are doing is you are having so the we are checking how the pressure changes with respect to uh, the change with respect to scaling of length. So basically now the pressure due to weight. So weight is basically mass into gravity. So basically mass is your density into volume. Then you have the area. So weight upon weight per unit area. So you do the substitution, and in the end what answer you will get is basically the pressure is basically scaled by length L. So change of length, change in the length by divided by 10, the pressure will also be divided by 10. If you change the pressure by if you change the length by by a factor of 100, pressure also will change by the factor of 100. So basically it is a linear relation between the pressure and the length. I hope this question is Understand. We move to the next question. Here you can see the system. Basically you have here I can see from the figure below you have like a central object, and it is being held in place by four beams. You can see here each beam basically has the same properties. So basically it has the same length L, it has the same width W, it has same out of plane thickness H. Suppose that each beam has a Young's modulus of y, then obtain the linear stiffness of the moment for of the proof of mass is y direction. So basically now this is basically you have to identify whether the springs are in uh, series or parallel. So this is something which you have to do. So these are the options given to you. So I give you some time. If you have a pen and paper, you can solve this question and come up with the answer. This is a very simple question. If you don't have pen and paper, I'll move forward. So just let me know. Anyone got the answer? See the K formula for K is W WHE upon H. So the formula of K is given. All you have to do is like find out. Even if you do it in the terms of K, it's fine. Whether you what is in series, what is in parallel, whether it is in series or whether it is in parallel. That is the only thing which I'm concerned about. And the key thing is basically the key point is basically here in here that basically
Sir, where is the K formula, sir? Here it there
K,
is no K.
K formula I'm telling you no that like uh, oh yeah here they okay, so since here it is the Young's modulus. So basically Young's what happens is there are two formulas. So that the previous one was the formula for E. When the elasticity is given, so elasticity cross sectional area cross section into elasticity upon length. So here what happens is you have to go with the moment of inertia. So basically in this case what the formula will be based on the moment of inertia. So the formula for K is basically given by y, that is the Young's modulus into. So basically now here the deviation is basically what we are doing is we are finding along the transverse like what we are concerned with is the transverse direction, right? So that is why the what you will get is WQ. So if it was so the force here is in this direction. So force is along the length. Okay. The if the force was in the like uh, in the opposite direction. So if it is now what we are doing is we are finding around the y-axis, right? So y-axis, what matters is the w. It will be the w cube. If it was along the x-axis, it would have been h cube. So in the same formula, if you can see here, since we are calculating along the y-axis, it is the w cube. So that is the out of plane thickness. So otherwise, it would have
Sir,
been.
I need some clarity, sir. Please again repeat, sir. Along the y direction.
It is yeah. So along the y direction, the formula is w. You can see here y is in the like uh, it's this way. So I'll just transfer to you. So this is the cross section we are talking about. So see, the out of plane thickness is this h, right? And this is width is w. Okay. So here what is happening is the moment is happening along the y-axis. Okay. So when it is happening along the y-axis, so this is the y-axis, so it will be w cube in the formula. Okay. And when it will be along the x-axis, it will be h cube. You can see the formula here. See, it is W H Y cube into H. So Y is the Young's modulus. Okay. H is the, which as I told you, if it is along the y-axis, if it is if it is along the, so this is the y-axis, right? This is H and this is W. Okay. So when it is along the y-axis, it will be W cube. When if you are taking the moment of inertia along the x-axis. So per se tomorrow your force is in x-axis in your exam or somewhere. Your force is along the x-axis. So that time this one will be in the cube and it will be W. So the formula will be y w h cube upon l cube if it is in the x-axis. So this is something a shortcut I'm giving you to remember it. Okay.
In whichever direction the deflection is there, that will be the cube, W cube, sir, here in this case.
We are not talking about deflection. We are about the moment of inertia. So when
Okay,
we
sir.
are finding a moment of inertia, see what we are doing. What this is the formula for WH cube upon L cube is the formula for moment of inertia.
Okay, sir.
YH cube upon L cube. Basically, it is Ki. The basically Ki upon L. So what see the stiffness formula is basically K is equal to Young's modulus, that's EI upon L. So that basically the what the formula will be of Young's of the moment of inertia. So I'll just draw it out. So as not, I'll just type it out. I'll just type it out in the comment section of the answer only. Is K, basically K is equal to E. So in the comment section, you can see the formula. So basically, the spring constant is basically Young's modulus into moment of inertia upon the length. So now the formula for moment of inertia is equal to uh, uh, BHQ uh, by L square. So um, whatever. So as I said, as I mentioned earlier, if it is in the y-axis, so it will be W uh, cube into h. So h into w cube upon l square. That will be the moment of inertia across the over the y-axis. About the uh, z-axis, about the x-axis, sorry, it will be uh, h, w h cube upon l square. Okay. It's are you able to like will you be able to understand it?
Yes, sir.
Okay. Then basically now what is happening is basically since we have to here we have to find out the deflection in y direction. So here what is happening is across the y axis the mass is moving. So what will happen is all the beams will deflect in the same angle, right? The angle of deflection. What will happen is basically uh, all Here, when the body will move here, body will reach here. What will happen is this beam has reached here, this beam has reached here, this beam has reached here, this beam has reached here. So what is happening? Deflection is same. When the deflection is same, the beams are in parallel. Okay. So when the deflection is different, so if the reflection would have been different, then it is they come in series. So here, since all the deflection is in parallel, so what we are getting is basically 4K. So that is the total spring, sum of the spring constant of all the beams. That is 4 into YH cube upon L. Okay. Are you able to understand this?
Yes, sir. But any link for theory, if it is available, please share, sir.
It's
So that later I can see the derivations somewhere in any textbook or any
yeah, yeah, I'll do it.
website link.
I'll do it. I'll do it. Don't worry.
Okay.
And I think so in the class sir explains it in the lecture. If you go through it, sir explains it. I think so. When I first I saw this lecture quite a long time back, so I don't remember exactly. But yeah, I think so sir explains it. Although I'll give a good reference material in the drive link only. I'll do it. Okay. So I hope this question is clear. So we'll move to the next question. So this is the question number 5. So here you have another system, the similar kind of system you have. The length of each beam here is 150 micrometer, width is 30 micrometer, out of plane thickness is 50 micrometer. Suppose each beam has the Young's modulus of y is equal to 130 gigapascal, then obtain the linear stiffness of the beams in x direction. So now the motion is this side. Okay. So earlier the motion was the upstairs, now the motion is this side. Okay. So now the formula here you can see, um, here we are having a spring. Okay. So here the formula is WH y HW upon L. So this is basically we are having the elasticity. So basically it should have been elastic modulus. They have given Young's modulus here, but it is wrong. Basically they have to give elastic modulus here. So the formula what they have adopted is basically elastic modulus into area upon length. So what we are getting final, by using that formula, we are getting the k value. Since now what is happening is, um, uh, all the beams basically uh, are moving in the x direction. So basically, these two are parallel. The deflection that these two will have, so will be equal to the like negative of the deflection of these two. So if these are deflecting from here to here, if they deflect by delta x, these beams will also undergo deflection of delta x. The total when the deflection is the same. So when we consider the springs are in parallel, when the deflection is the same, although it may be negative delta x, so the deflection by all the springs is the same. So here that is why what we are doing is basically the we are considering all the beams are in parallel, and that is basically what the total sum of stiffness is basically 4 into k. That is 4 into the linear stiffness of one beam, and that is 4 into 1.3 into 10 raised to 6. That is 5.2 into 10 raised to 6. So here there has been some problem with the question framing, because the formula that has to be used is this one, that is the K. So there is one is EI, A is equal to EI, or basically the second is equal to K is equal to E into A by L. So if you actually do the dimensionality, so is basically if you take out the dimension, so basically uh, you will get so here like in the previous question what we had, there we had W cube upon H into L cube. Okay. So the formula, like the what you are getting is basically you are getting the same answer. So dimensionally it was the same thing. So that is why what you are doing. But in this question, you have to use this formula. So that is the y into cross section upon L. I know it is a bit confusing for many are not from the electronics background, who are not from the mechanical background, but I, I it's how it is. So any questions with the like parallel series? Any question with this in this question? So the formula, leave it aside. You will get the formula in your exam most probably. So just whether you understood it was parallel and series or whether you have doubt on that. Can you like anyone have any doubt with parallel series? We'll break it down first. So anyone has any problem with like couldn't understand why it is we are taking parallel and why it's not in series? Any
Sir, where is the application of this model, sir?
uh,
In the real time, where is it,
can you be louder, please, sir?
sir?
Your, just a second. I just turn on my volume. Yeah. Yes. Hello. Yeah, ma'am. Can you repeat your question, ma'am?
Sir, where can I find the real time application of this type of element?
So actually, these kind of things are basically used in accelerometer. So accelerometer, like not completely, but
Okay, sir.
accelerometer basically what happens. I'll just show draw and tell you how the accelerometer works. So yeah.
So to increase the stiffness, it is one of the methods, sir.
Yeah, there are many applications, but I'll just show you how an accelerometer works. So basically, what happens is in an accelerometer, when the acceleration happens. So this is capacitor. So this is a capacitor with C. This is a capacitor with C. This is a capacitor with C. So when an acceleration happens, so when the car is moving, and when the acceleration is the change in velocity. So what will happen is this will move straight, and this is fixed. This comb is fixed, and this comb is like moving. So what will happen is the distance between these two will change. Okay, distance will change, distance changes, and then what you get is the capacitance changes. Uh, and when you get capacitance change, that is converted into acceleration. So earlier, so now this is used in a you are using a capacitor model. Earlier, for this case, what they used to do is they used to have a piezoresistive model. So it used to go straight. Okay. So what you will experience is when there is a change. So when the motion is happening, what you will see is you will see the deflection happening, and so your deflection obviously it's a piezoresistive sensor, so you will have the resistance change, and resistance change obviously you can get the acceleration. Okay. So earlier this used to be there, but now what is happening is because of the moving element. So this what we saw in this question, because of this moving element, because it has a mass, it would have an inertia. Okay. So any body of mass has some inertia, right? So because of the mass being higher, it had inertia, and that is would give wrong readings. So that is why then they switched to capacitor. But now since we have to understand all the principles, right? So in this course we are understanding this principle. So actually this principle was used earlier in the capacitive sensors. Uh,
Sir,
cap-
which is accurate one, sir?
huh?
Compared to two different models,
Acceleration
which
is
is
your voice.
accurate one?
Your voice is
Which will be the accurate reading, sir?
hello. Ma'am, your voice is breaking.
Sir, which will be accurate reading, sir? Is it
Yes.
piezoresistive type or capacitive?
So this is a piezo-resistive type in the earlier one. So because of the inertia, uh, the reading would be bad. So that is why they moved to capacitive type. So this is more advanced. Capacitor type is more advanced because there is no moving part. So anything that has limited number of inertia, so when the mass is low, the inertia is less. So that is why the capacitor base is more accurate, whereas the this piezoresistive one is less accurate, because what is happening is this block, this big block, although it's big on the micro sense, huh? We are not talking about the law, like big means very big, but because of the inertia, it would it would not come back to its original position that easily. So that is why it would not give that good reading, whereas a capacitor will give better reading, and it can also be used, because what will happen is the capacitance type, it will have so it will have like four. So it will give also directional accuracy. So it will be like this sort of, but you cannot get, so if it is moving in this direction, this one will like you can see from based on the direction also, the movement will be different. So if it is moving in this direction, these two things will move, right? These two uh, this is a fixed plane, this is a fixed body, so if it is moving straight, these two will move, right? A and B will move. If it is moving in the right direction, B and C will move, and if it is moving the left, then A and D will move. So what will happen is, in with the capacitance space, you are able to get the directionality also. In this case, you are only able to get like front and back, right? You are not able to get right and left using this structure. That is why the more accurate one is the capacitor one. But this is, nevertheless, we have to study it, because it it is from where everything has evolved. So you need to study. Any question? Any other question? Okay, so we'll move to the question number 6. So here we have a rectangular beam of length L with W and out of plane thickness H. The beam is attached to one side and free on the other. The linear stiffness constant of the beam in y direction is K1. Now, if we increase the width of the beam to 2W, what will be the new linear stiffness constant of the beam in the y direction? So basically, we have a beam, and now we are asking that how will the stiffness constant, well, how will the K change if the width of the beam is changed. So here it is. So basically the K value here is basically we are using the moment of inertia formula. So that is y into h um, um, hwq upon 4L3. So now why is there a 4 here? So basically this is basically these formulas, K formulas, are given in your are given in the class. So basically, because this is a single-sided support, so this is fixed side, and this is free moving. So the formula here will come at so there is why there is a 4 here. So depending on how the body is, if there is a both the side, if it is here, then the formula will be changing, then it will be above uh, 4 L cube upon 128 or something. So the formulas will change. You will get those formulas in your in your lecture notes. So you just go through it. The formulas are there in your lecture notes. You need to by heart those formulas, unfortunately. So here we have the K formula, which is already been given, y WH cube upon 4 L cube. Then we change the width from W to 2W. So what we see is, basically, because it's in the along the y-axis, uh, width will change by 2W. So as I said, um, um, because it's along the y-axis. So here what is happening is, here we have W and y. So just taking the cross section area. So W, y axis, and this is H. So Q, right? So we had discussed that earlier in that I had given the shortcut. So the answer, so you are getting the formula as y H W cube upon 4L cube. So it will vary by the cube, by cube, it will get cubed. So the answer will be 8k1. So the answer here is 8k1. I hope you have understood it.
Yes, sir.
Yeah. So these formulas you need to you will find in your course notes. Whatever that are relevant to the exam, you will find in your course notes. If not, just let me know in the last in the revision section in the last week. I will bring those formulas with you. So moving to the next question. The two springs are connected in series. Assume that the mass is pulled in x direction. Which of the following entities remain same in both the springs? The stiffness constant of the spring, the increase in length of the spring, the applied force, none of the above. So basically, uh, we have something like two springs are in series and the mass is moving. So what it is asking is whether the stiffness constant of the spring will move. No, basically the stiffness constant, as you saw, is basically the material property and the dimensional property. So it is not necessarily that if it is in series or if it is in parallel, you will get the same like stiffness constant. The stiffness constant is basically a material property and the geometrical property. It is not the configurational property. Again, then the change in length, not necessarily, because the change in length is dependent on the stiffness constant. It is not dependent on the force applied or on the configuration. So the answer is the force applied. So basically, the amount of force. So we all know the force transmissivity law. So for every action, there is equal and opposite reaction. So amount of force that is applying here, being applied here. So basically, F, F, F. So basically, the since it's in series, the force is getting transmitted. So the transmissivity of force, the force applied on each of the springs will be the same. The deflection need not be the same. In parallel, the deflection is the same. The force is not the same. So that's how the thing changes. So I hope everyone has yeah, understood it. Moving to the next question. In the following spring mass system below, four springs of the stiffness K2 and K3 and K4 are attached. What is uh, the displacement if it is displaced along the axis of the spring? The axis of the spring, here you can see, axis of the spring is here. Okay, so assume that this mass is displaced along this axis. So like here the deflection will be delta x, and here again this because it is here displacing this way, there will be delta x or minus delta x. You can whichever way, whichever the like whichever convention you like to use. So what will be the stiffness constant? So what is the configuration you will use? Whether it is series or parallel. The deflection is same. So what is the configuration? Whether it is a series configuration or parallel configuration. It's a parallel configuration. So since all the things are in parallel configuration, the equivalent stiffness is K1, K2, K1 plus K2 plus K3 plus K4. So here you can see here first find the equivalent constants for left side, then right side, and because the change in length. So here, as I explained it to you here, the deflection is the same because it is happening along the same axis. The deflection here is same. That is why what you get is the total stiffness constant is K1 plus K2 plus K3 plus K4. So again, this is the same question as what we did earlier. So we have here a glass cube. It has the density of 2500 kilogram per meter cube, and we have to find the critical length here. But the surface tension of fluid is changing, and we have to measure the point. So the same thing. what we have to do is the surface tension force has to be greater than the weight of the block. So use the formula for surface tension force, you use the formula for weight of the block, you substitute everything, and then you come up with the answer. So the answer is 3.94 millimeters. So moving to the last question. So here, this is the free body we have to get the free body diagram of the configuration. So basically, you have a fixed beam here, and you have a slider here. So, uh, so basically, what will be happening? So let's take this side here. Okay. So what will be happening here? So now, whenever any force is applied, okay, just assume any force is being applied. So what will happen is this wall will give back force, right? Whenever so per se I'm applying force from here. So just visualize it, okay? So now we are just taking this side. So wall will when you are applying force from this side, wall will apply. So here is the wall. So wall will apply reverse force because wall has nothing nowhere to go, right? So when the force is being applied, wall has nowhere to go. So since the wall is stable or wall is static, it has to apply opposite force so as to like maintain its position, right? The same thing if some force is coming from here, okay, top. What will happen is it since it's a fixed end, it cannot move. You cannot move it downwards. So what will happen is there will be force applied by the wall itself. So wall will apply opposite force so that the beam doesn't move or go down basically. And now the last thing is if you are motion. So basically if you are time moment, so that is called moment force. So basically if you try to bend the wall, bend the beam basically. So even in that case, the wall here it is solid, it is static in nature. So the it will not bend also. It will not move. It will not get deflected also. So for that, wall will apply a counter moment. So the so now what you get here is uh, force in the x direction, force in y direction, and also a counter moment. Okay. So now let's take this. So here, what is going on? Okay. So here, per se, if it is a slider. So here, what will happen is if the beam is basically I apply force from this end. What will happen? Nothing will happen. The slider will not do any counteraction. So there is no force applied by the slider. So again, if I apply a moment here, if I apply a moment, nothing will happen. The slider will allow it to like bend. Okay. So since the slider will allow it to bend, so there will be no moment from the slider also. But if I apply a force from this direction, what will slider do? A slider will like repel, right? Slider will uh, not go like slider will not necessarily go inside the wall, right? It will be stable at that place. So the answer here is D. So here you can see this side you get the force applied by counter force applied by for all the three direction, but in this case you'll get counter force applied only in one direction. So any questions with this? Any questions? We are done. So any questions with this problem or any other questions in general? We need to we will be winding up. So any other questions in general? Anything about like the course? You can just ask me. Any questions in general you want to ask, please?
Sir, if any doubt is there, how to send
So
how to send up
yeah, so there are there are two three methods. So one is you can best method is basically you have to use the discussion forum in the course. So give me a moment. I'll just log into the course and I'll show it to you.
The other one is the other one is
Other one is basically like you can ask us, but the thing is, like we are supposed to like just help you with the assignments. So, and we
in
will
the
also be,
interaction section, sir. In the
yeah,
interaction.
yeah, you can ask us in the interaction session. But what the thing is, we are also limited to what we like we prepare.
Okay, sir. Okay, sir.
So I'll just show it to you. Just if you can just
Maybe in the forum, our question may be a silly question.
yeah, you can.
Later, we may feel that's why I'm asking.
Yeah, you can ask us. You can ask in the like what we'll do is you can ask first in the discussion live interaction session. If
Okay,
we are
sir.
not able to answer, then you can ask. We'll only tell you that okay, ask in the forum. We are not able to
Yes.
answer because
Okay. Yes. Yes.
so
Thank you,
that
sir.
way we'll do it. Any other questions? If you don't have any other questions, you can. We are. It's already about 8, so we'll end the session. So anyone has any questions, please let me know. I'll wait for another moment and then we'll end the session. Okay, so since nobody has any questions, um, I'll maybe end the session. And my voice has gotten. I'll end the session. We'll see you next week. Thank you for your attention. Thank you for giving your time. We'll see you next week.